Recording is rolling. It is Tuesday, September 24. Quick update on your projectile quizzes. Most of you guys turned this in about a week ago. I'm still waiting for a few from each class before I hand those back. So double check focus, make sure you have turned it in. Some students think they turned stuff in. It's actually in the folder, so check that. All right, so Friction Lab. Today, you guys are doing a Friction Lab. I just handed you guys this page right here. This Friction Lab is going to be in two halves. Talked about this a little bit yesterday, but I'll remind you guys how this is working. Right? So there's a left half and a right half. All right. Now, guys, by the end of class today, hold on to this paper. Here's why. On the back side of this page is a different lab. This is Atwood Lab. I want to do this one later this week. Okay. Most students by the end of class today, I think if you keep a pretty good pace, you should finish the graphs and be able to answer the questions at the bottom too. But if you don't quite finish it, then that'll be right, because you guys can hold on to this anyway. Right. So, there's also a direction floating around how to do this lab. Yeah, there's two halves, the left half and the right half, which I'll break out some posters here in a minute and show you guys what each have it. Right. But if you want some directions that you can follow, that you can read and follow, here's the left half, here's the right half, exactly the procedure for each one of these. And I'll pull out some posters and show you guys exactly. And then on the back is like some analysis and some math, how to get to the conclusion. I'll do. All right. So this is floating around, and then you guys are, of course, recording on your table right there. You guys got table, graph, and a couple questions. All right, so what's going on with this friction lab? So your guys' goal today is to determine what is the coefficient of friction. Isn't that, I should have asked you guys. Guys, we said this is coefficient of friction, right? And the K could be kinetic if it's sliding, right? So coefficient of kinetic friction between two surfaces. You guys got a box of lab weights and whatever surface. So pick your favorite surface. Could be the lab table. You could pull out some paper if you want to drag it across paper, that's okay. It could be the surface of a textbook, that's okay too. Okay? And it turns out for this entire lab, and it says this also on these directions, you only need a couple of tools. So the one way, the left half method, you only need a spring scale, that's all you need. The right half method, you can do entirely with a protractor, well, as your measuring tools anyway. Of course, you need the lab weights and some kind of surface and the whole deal. Right, that's it. All right, so guys, this right here, I'm going to leave it up to the first half of class, because this is the left half of your lab paper. This is the first half of today's lab. Okay? So notice here the title says you're pulling at constant velocity. You're pulling horizontally with constant velocity. Guys, why is constant velocity important? Constant velocity means what else in physics? Zero acceleration, which means zero net force, which is a type of equilibrium. Equilibrium might be at rest, or equilibrium might be constant velocity. Okay, at rest is, well, that's the static situation. There's an inequality. It's a little trickier. Right? But hey, if it's sliding at constant velocity, that's a kinetic case. I can always say equals. Okay, this is a little more straightforward. Okay? So, because when you're pulling at constant velocity, remember all the forces cancel out. This is what should be in your mind, and what you guys are gonna see on the projection anyway. And maybe I'll ask a quiz question. Have you guys draw this free body diagram? That could be a good quiz question. Right? Pretty straightforward. Draw the free body diagram for pulling a block across the table horizontally at constant velocity. Okay, well, the block has a weight. There's a support force from the table called a, what kind of force is this? Normal force. Now you're applying with some applied force, I'll call it. You're pulling, right? Do F sub pull, that's okay too. Okay. But if that's all you had, it would be accelerating, wouldn't it? Zoop. Right. So there must be a force resisting that called the what force? Friction force. Now, this coefficient of friction, this is your guys' goal today. Determine what is the coefficient of friction between these two surfaces, right? Say like a lab weight and a table surface, for example, right? Is the ratio between these two forces right here. Is that friction force over normal force? Okay. Now, it turns out that's a material property. So once you know the material surfaces, like if you have like this painted surface against paper, for example, right? There should be probably some consistent ratio, right? You guys got that? Right. Maybe that'll show up in the graph that I'll have you guys graph later. Speaking of the graph, let's get the graph real fast. Okay. I threw you guys titles on these graphs. I've been getting some good questions from my classes earlier today. One of the questions has been, what variable goes on which axis? I got pulling force versus weight. Guys, is the title always y versus x? Right? Y versus x. So whatever I name first goes on the vertical, and then versus whatever goes second goes horizontal. Right? It's always y versus x. Okay. Right. So you guys can graph that. I've been looking today. Students have had some pretty good graphs overall. So, of course, I'll be walking around, troubleshooting any questions you guys have. All right. So there you go. All right, you guys ready for the second half? All right. About halfway through class, I'm going to switch over to, okay. this is in your notes from yesterday, right? You guys remember yesterday, we took some time, you guys drew this in your notes, right? Now I'm gonna take exactly this, I'm gonna shrink it up in the corner a little bit, but it's the same thing. Okay? Guys, sliding at constant velocity, hey, constant velocity, that's zero acceleration, zero net force. Now I can start out this proof, and you guys see it's like a chain of dominoes. I think we talked about this yesterday. Okay? But at the end, you can also get coefficient of friction. Now, I was really debating, should I show this or not, right? If I really wanted to challenge you guys, if I wanted to make this like a 2 or 3 day lab, maybe I wouldn't give this to you at all. I'd have you guys figure this out from scratch. But here's maybe the end result, right? But ideally, if you want to get the most out of this class, see if you can maybe pull out a blank piece of paper and maybe solve this whole proof from scratch, right? But I'm sort of telling you this should be the case, right? But of course, experimentally figure this out. So here's how this works. Find some surface, maybe ideally the same surface as you were using before. Right? Could be your desk, could be a textbook. So be creative with it, right? And then what you'll do is you'll put a lab weight on top of that surface, and you'll tilt that surface, tilt until it slides down at constant velocity. Constant velocity, equilibrium, but we're also finding something about kinetic friction. In this case, coefficient of kinetic friction. This is all leading to. Right? You guys good so far? Right. So your sort of independent variable, if you want to think of that way, could be the lab weights. You can pick all different lab weights. It's okay. Ideally, have the same surface. Technically, these are different surfaces. You got paint versus bare metal. Sometimes in the past, I have students coat these in paper or something, but you guys figure that out, what you want to do. I don't think it makes too much of a difference anyway. But guys, this angle, you're going to naturally just tilt this until it naturally slides down at constant velocity. And whatever that angle naturally is, okay, just record that angle. Okay. Protractor, I'll help you guys use the protractor. Guys, reminder how to use the protractor. What you're trying to do is figure out what is this angle here, right? What is this angle? So, you guys remember this node of this protractor right here? Do I want to measure here? Let me do one that's wrong. Can I say, oh, just throw the protractor anywhere, just throw it anywhere, and say, oh, look, this looks like about, oh, what is this, about 60 degrees? Guys, does that look like a 60-degree angle? Nowhere close, right? Guys, this node needs to go out on the corner. So if suppose you use a textbook, maybe you can use the bottom edge of the textbook. You want to make sure that the node, say, goes through the bottom edge, and then the bottom edge also sweeps through what the angle actually is. So notice this is zeroed out, horizontal flat, maybe using flat on the surface. This node is parked right on that corner. This node needs to go on that corner. Or if you use a textbook, maybe this could be the bottom edge of a textbook. And then this naturally sweeps through. This looks about, somebody aligned that a little better. Looks about 27 degrees, I'll call it. So on my paper, it's about 27 degrees, but when you guys do the lab, it's whatever it is. Okay, you guys get that? Right. Then just follow the page. It'll tell you certain calculations to make, certain graphs to make. I'll walk around and help you guys out. Students have been doing pretty good on this today, and I'll answer any questions you guys have. You should probably be able to finish within about this class period, but if you don't, that's okay too, because I want you to hold on to the paper anyway, so we can do the Atwood lab a different day.